Hello, everyone. Welcome to today's exciting webinar, which is our second of 2021. I am Tim Stark and the host of today's exciting event. I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign and technical director of the Fabricated Geomembrane Institute. This is our second webinar of 2021, and the remaining 10 have already been scheduled with great speakers and timely topics, which are available on our website. And the next webinar will be announced on the last slide today. During today's webinar, we welcome your questions and comments, which can be typed into the questions box in the control panel. You may send in your questions at any time during the presentation, and our speakers will address them at the end of today's presentation. The recording of this webinar and a PDF of the slides will be made available on the FGI website after today's presentation. PDH certificates will be sent automatically to all who attend the entire webinar. Okay, today our webinar speakers are Duff Simbeck, Brendan Simbeck, and Pat Elliott. Duff Simbeck will start today, and he is Vice President of Simbeck and Associates. He has been involved in the field installation of geosynthetics and project management for 22 years, with projects ranging from North Carolina to California. Brendan Simbeck is project manager of Simbeck and Associates in Monument, Colorado. Brendan has been installing geosynthetics since 1998 and has installed over 52 million square feet of geomembranes across the United States. Pat Elliott is the director of installation services for Raven Engineered Films through their subsidiary Raven CLI Construction, Inc. Pat is also the current president of the Fabricated Geomembrane Institute. The title of today's webinar is Geomembrane Attachment and Penetration Design and Installation. Duff, Brendan, thanks for squeezing this webinar into your busy schedule and joining us from Colorado. So Duff, please proceed.
Thank you, Dr. Stark. Everyone, on this first slide, please skim briefly the focus for the next 40 minutes. I get the easy part because I'm the least experienced of the three presenters. We'll try and get through these slides gradually, but there's the focus. The consistent emphasis, of course, is addressing the most important quality control aspect. We've broken it out as you see on the third slide. Brendan will cover the first section about the pipe boots. We're going to move on and talk about the mechanical attachment. I've got a short section to cover with the anchor trenches. Though it's not a penetration, it's an important part of the liner system, and of course that's worth mentioning as a support to make sure that everything's secure. And then Pat has the heavy lifting. He'll cover the last section on embedment strips. All right, our first topic, everyone. We've got 22 slides coming on the basics of pipe boots. You'll see these slides later. Just a quick introduction. We'll also cover some of the steps on the quality control. Note, please, the fundamental parts to a pipe boot. The skirt, the tube or the sleeve, the banding, the last seal, and of course the primary geomembrane. And Brendan will take it from here to focus on the pipe boot details.
All right, thank you, Duff. So, we went over the basic parts of the pipe boot. Now, Here's a couple of very basic detail drawings of pipe boots. I will mention also that there's a variety of these detailed drawings available at the FGI website, as well as a lot of the installer members. Their websites have libraries of these that are available. So here, when I'm looking at pipe boots, I generally group them into 90s, shown here on the left, and slope boots. So a 90-degree boot is pretty basic. You got your tube and your skirt, with your big variations being the pipe diameter, the size of the pipe. On the right here, you got a slope boot. Now, slope boots are going to be unique to both the size of the pipe as well as the grade of slope. The fact that these are installed on a slope is also going to present some access issues, particularly in what is called the throat area, the underside of that pipe. This is really where you're going to have your most important critical weld between the tube or the sleeve and the pipe boot. More often than not, if you do have leaks in a pipe boot, this is going to be the location where you're going to find a lot of them. Moving on here. In this detail drawing, we have a pipe collar, a cement pad that's poured around the pipe that's penetrating into the cell. What's good about this is two things. One, it really holds that pipe in place. It prevents any movement of the pipe, and it also gives a real firm, solid backing to the pipe boot that can be installed on top of that. You know, it won't be prone to sloughing off or displacement of the soil at and around that pipe. Now, in this picture on the lower right here, there's not actually a pipe boot installed. This uses mechanical attachment in lieu of a pipe boot. But I will point out that anytime you have a situation like this, it's very important that you have some sort of a water stop between the OD of that pipe and the cement itself. You need to make sure that you have a leak tight seal so that you don't have any leak path there at that point. If we could advance to the next slide here, there we go. So here we have another detail. In this case, it's a double banded pipe boot placed on top of that pipe collar. Now, this detail here actually calls out for mechanical attachment in addition to the pipe boot, which is a good idea in theory, because that really, it prevents any stress in the liner being focused onto that pipe boot. The downfall is that by drilling and installing those anchor bolts for the mechanical attachment, you're actually penetrating the liner more. As a rule, the fewer penetrations you have through the liner, the less risk you have of developing leaks at those locations. So I like this picture here. This is a before and after of a pipe penetration, again with a pipe collar. This pipe collar has embedment strips set into that concrete, and then the pipe boot placed over top of that. This is a great configuration. I think Pat's going to talk more on this later on when he touches on embedment strips, but this is a really a good situation I like seeing here. So when it comes to building pipe boots, you really have three options, the best of which is having those pipe boots prefabricated. That gives you the ability to build them, you know, on a workbench using fixtures, using jigs, so that you can, in a controlled environment, so you consistently get a higher quality product. Those can be welded, they can be tested, and then they're shipped out to the job site for a quick installation. You know, greatly reduces the time on site installing those pipe boots. The problem that often comes from that is when site conditions don't exactly match the design parameters. If you have obstructions, bells, flanges that you need to install these over, or if your slope grade is slightly off, then that's going to affect the fit of that pipe boot, which leads you to either modifying the pipe boot in the field to fit those conditions, or scrapping it and field fabricating a boot, which takes more time, but it can be built around those unique situations that as they're constructed in the field. The third option is kind of a hybrid of the previous two. It's a partial prefabricated pipe boot where you take your tube or your sleeve and your skirt, and you weld and test that critical weld through the throat area, joining those two pieces. You can do that in the controlled environment, so you kind of get the best of both worlds, a controlled environment for the welding of the critical areas, but by leaving that tube open, that also allows you some adjustment when you get out into the field. If your slope grade is slightly off, you're able to accommodate for that by adjusting that final weld that'll be completed in the field. You also have the ability to install over top of flanges, bells in the pipes, situations like that you encounter in the site. It only leaves a simple, very accessible weld to be completed in the field. So that's just kind of the best of both worlds, like I said. So here we got a handful of pictures of installed pipe boots, some 90s, some slope boots. A couple things of note: you see there's some wrinkles in the primary liner. Everything's well form fitting to the pipe, to the slope. That liner's really in a relaxed state. So these are good examples of installed pipe boots. So when you are installing the pipe boots, like I mentioned earlier on that last slide, it's important to have a snug fit to the pipe. It's also very important that you match those slope contours with little or no bridging of the material. And a key factor that always needs to be taken into consideration is the thermal changes. Materials are going to expand and contract as the temperature changes. Some materials much worse than others, but it's always something that needs to be accounted for when you're installing these pipe boots. Best practice after you install the primary liner is to allow that liner to go through a couple of heat cycles. That way it can expand, it can contract, it really settles in, it finds its home before you fix it to that location by attaching the skirt or banding the pipe boot. When it does come time to attach it and band it, if at all possible, you always want to do that in the coolest conditions possible. That way you can catch the material in its contracted state before you lock it in and fix it to that location. This last point here on the slide should go without saying. Anytime you're welding liner, you need to have it clean, you need to have it dry. Good prep makes for good product. Banding. So when you're sealing the end of the tube or the sleeve, you have a cutaway picture here of the basic banding materials. Starting on the left-hand side, you have your butyl tape that seals between the pipe OD and the membrane liner. Next layer, you got your membrane liner. On top of that, you have a cushion layer of a live rubber, a neoprene or EPDM, directly below the stainless steel strapping. Now, on the upper right there, you'll see to cap it all off, to seal those end faces, you'll apply a bead of polyurethane caulking. So when it comes to strapping material, on your right here, you have a worm gear hose clamp. These we see failing all the time in the field. This is really not appropriate for use banding pipe boots. They just don't last over time. You don't have that strength you need to get that good compression seal in the banding area. On the left, you have a Bandit brand tool, strapping, and clips. This is really a fantastic product for banding pipe boots. Super strong, will last forever. Highly recommend this type of a setup in lieu of the hose clamps. Once you have your pipe boot built or installed, then you'll need to non-destructively test it. So quality testing of the pipe boots, you really have all of the methods that are available for the primary liner. You know, your air lance testing, your spark testing, your vacuum testing, as well as some alternate methods, a probe test or a pick test, a visual inspection by a well-qualified technician or QC personnel can be very effective, as well as water balance testing. So here we got a quick video of an air lance test. What's nice about this method is you have both an audible cue as well as a visual cue or indicator of a leak or a void in that weld. Here we have a spark test being performed on an extrusion weld from a geomembrane liner to an embedment strip that is set in the concrete. You'll see where that arc was created there. I think we'll come back to it. It's pretty clear where the leak is in this weld. Here we have a short video of a vacuum test. Now here you'll have a visual cue. You see those bubbles developing in the soapy solution right in the center of the slide. That's your cue or indication of a leak on a vacuum test. Here we have a probe test or a pick test. It's a pretty straightforward, a manual inspection looking for any voids along that seam edge. So now let's talk about some pipe boot failures. You know, here we obviously have some catastrophic failures of pipe boots. You'll see on the left-hand side, you see that liner in the backdrop there is super tight. There's obviously some stress there, some bridging. If you look through that cavity, that opening, you could tell that the liner is pulled away from the subgrade. The banding has failed. I think this is a hose clamp type band that's down there lower on the pipe. So this is an example of a failure due to movement of the liner. If we go to the next slide, we'll actually see underneath what caused these failures. Water had got behind this liner, eroded the embankment, which left that trampolining or bridging of the liner. Now, any movement from wind or stress from that liner then was focused on those fixed locations at the pipe boots, which eventually just beat them to death and caused the failures we just saw. So here we have another couple pictures, pipe boots installed. On the right, you'll see that that bolted flange is just inches above the subgrade. You know, that gives the technician a very small working envelope to be able to build that boot in place, weld it, test it, and band it, just in that 6 inches or less of surface you have to work with. On the picture on the left here, you'll see there's definitely some tension in the liner. There's some bridging that you can see, and again, all of that stress from the liner is going to be exerted right on that critical weld between the skirt and the sleeve of that pipe boot. Here we have a couple leaks that were developed on the tube or the sleeve. On the left-hand side, right at the apex of the pipe there, you'll see there's a wrinkle in that material. That was a fold over that was captured underneath the banding, which allowed for a tunnel or a leak path right through that point. On the right-hand side picture, you see there's about a baseball size opening between the tube and the pipe. And again, those hose clamp type straps that obviously weren't sufficient in this instance. These are examples of not well-fitted tubes to the pipe. You have that extra material there, that's an opportunity for a leak path. I will also point out, this is a good example of, you see the flanges and the bells on the ends of those pipes. This is a situation where if you have prefabricated boots that are shipped out to the site with the intention of just sliding them on for a quick install, these kind of obstructions are going to affect that, the efficiency of having those prefabricated pipe boots. Here we got 3 pictures of some problems that are regularly encountered. I'll try and go through them pretty quick. On the left, you know, obviously that pipe isn't protruding out far enough to install a boot and get a good banding job done to seal to that pipe. We really need to have 12 to 24 inches of pipe exposed, particularly on that bottom side in the throat area, so that we can get a good solid seal of that banding. This middle photo is showing a grouping of pipes that need to have pipe boots installed over top of them. These are just inches apart. It makes it very challenging for the technician. In addition to that, there's a concrete pad on the right-hand side that's poured nearly clear up to that penetration. So this is difficult for any technician to get a good quality installation of pipe boots when you have that kind of congestion. On the right-hand side, this is a mooring post that's just inside from the anchor trench in a lagoon. This is an example of an item that penetrates the liner that, you know, quite possibly could be moved outside the lined footprint of the cell, relocated to the anchor trench, to outside of the pond, to prevent problems. Anytime you have a penetration through the liner, again, you're going to increase your risk of leaks or problems at those locations. Other items we see that don't necessarily always need to be within the lined footprint are, you know, manholes, bollard posts, pipe supports, valve boxes. Often those can be relocated out, which reduces your risk of leaks and problems. Here we got a couple pipe penetrations that are really right on top of cement structures. So you're going to have an intersection of batten or mechanical attachment right at the point of the pipe boot. This is going to be difficult for the installers and is really an example of poor coordination between the design team, the contractor, and the installer. You know, these easily could have been avoided to give you a better product in the end of the project here. Here we got some pictures of some pipe banks, some, you know, right on top of one another. Again, just difficult to get in there for the technician to weld, to test, to band. The challenging situation in all these pictures. So in summary, you know, it's critical for success that you have good coordination and execution from the contractor installing any pipes and compacting and prepping the subgrade at and around those pipe penetrations. That's going to be critical to success of the pipe boot. In addition, you need to make sure whenever you can that you provide as much access around that pipe penetration as possible to ease the installation of the pipe boot, and again, allowing that 12 to 24 inches of protrusion to get a good seal at that banding area. Pipe boots are going to be an area that is going to be prone to problems. So you absolutely want to make sure that you have qualified and experienced technicians building the boots, installing the boots, testing the boots, and you know, that's really going to increase your level of confidence in the project as you walk away from it. These last 3 points I think we've covered well enough. I look forward to any questions anybody may have or would like to submit. And with that, I will pass it off to Duff to talk about some anchor trenches.
Thank you, Brendan. Here are two designs we commonly encounter. And then our technicians, our crew will get to the site and they'll find something different from what they expected. So often a challenge is the contractor building it right to how it was designed. Sometimes it's a problem with the subgrade conditions, quality, and sometimes it's he doesn't have the right size bucket. But we work through that with hopefully a minimal amount of wastage by over digging a trench, for instance. And you'll see at the bottom a good resource. You can get all sorts of anchor trench designs from the FGI website and many other websites from suppliers and installers. At first glance, this is a great trench. I know the operator was pretty proud of it. It's very consistent, and moving from right to left, you see you have a pretty consistent, even subgrade prepped, and yet there's no setback. That setback, you'll see on the next slide, is something that most designers keep in mind to minimize the stress on that membrane system dropping down at the perimeter. They've got a clean edge here, but the problem on this first slide is we've got a bunch of spoils in the back, and that's a very inconvenient feature that we encounter often on job sites. Here, moving from right to left, we've got 2-to-1 slopes, and the setback is there, typically 1 to 2 feet, to minimize that stress on the edge of the liner there. And when it does drop down, you like to have that consistent edge. The contractor here didn't have a really good quality soil to work with, so you notice the cobbles. And even though he had the right size bucket there in the background, he overdug this. And on other sections of the trench at this project, it was 4 foot down and 4 foot across, which led to some wastage of membrane liner. And here too, you see that challenge we faced with the spoils on the back side to the left of this photo. Take a look and tell me what's wrong with this fundamental trench design. Going from left to right, I note it's 5 to 6 feet deep. And then they're asking the contractor to build it just 2 foot wide. Really tough to do to that depth. And what's the point of the depth? They've also asked that the contractor compact this in lifts. And we find this often, and it's really overkill, and it can cause problems to the membrane liner system because it puts stress when you're doing all that activity and pounding down those lifts. And occasionally we even see concrete pours in the perimeter trench. And unless there's something you're mooring to that concrete, we really think that's overkill. So the standard trench we like to see is typically a nice even slope up to the crest, and then about 1 to 2 foot of setback before the trench edge is cut. As consistent as you can all the way around on that trench edge. And then, of course, a regular amount of depth, typically 18 inches to 30 inches down, 1 to 2 feet across is typical, and then curling up the backside just slightly before the backfill. And again, practically speaking, it's important that we don't have those spoils up on the left side to get in the way of us deploying liner downslope. Passing the baton now to my friend Pat Elliott with decades of experience, and that's both in the field and from the design perspective, managing the jobs.
Thank you very much. Tough act to follow. Really great information, Duff and Brendan. That was fantastic. So I'm going to start out with basically going over these four design criteria of anchor trenches. So we'll start out with design materials, the common problems, similar format to the pipe boot and the anchor trench section, cover quality testing a little bit, and then we'll kind of recap with the key components to success. So yeah, let's get started. Next slide, Tim. So what you're looking at here is you're looking at two details side by side with a picture depicting what the difference is. And I always stress with mechanical attachment, it is always better to come in on a flat versus turning up. And like, for example, that picture on that left, that's on the vertical slope. And what you're asking the membrane to do is to turn up, and you're asking for a lot of corner welds and a lot of critical leak paths. And whenever I'm looking or helping design or working with an engineer to help design a membrane, the goal is always the quest to zero leakage. So the better quality details and eliminating as much hand welding and tight, intricate details and welding as possible is always the goal. So when you go in with a flat attachment, there is zero to little hand welding around that, and mainly just sheet membrane going into that mechanical attachment. What we got here is this is just a typical batten strip. This is pretty standard. A couple things of note: 6-inch on center holes or 12-inch. At my company, we always recommend if this is an underwater attachment, 6 inches on center is our standard. If you're going above water, we will allow it to go out to a 12-inch on center to reduce the amount of drilling and bolts and holes and costs and everything associated with that. Next thing you can see here is you can see the holes are slotted. That's pretty critical for pulling the bar on and off as you're doing the different steps of mechanical. Allows for some movement as you're installing that bar. In the situation where you're ever removing that bar and replacing a membrane, or taking it off to do repair work, or for any number of reasons why you have to remove that bar, it allows you to get that bar back on. It doesn't allow for such precise holes or alignment for the bolts with the holes. Also typical is aluminum or stainless steel. So that just really depends on what the application is for freshwater or chemical resistance, that kind of thing. So obviously the installers love the aluminum because it's quite a bit lighter than the stainless steel. Another thing I recommend is anti-seize. We always put anti-seize on the bolts. That way, if you ever have to remove it, it allows you to do that without damaging the bolts. Next slide. Here's a couple pictures of just standard bar. You can see there's slotted holes. A lot of times the critical things are you require distances to the edge of the bar. You can imagine if that hole is too far away from the edge, you don't get as much compression at the end of that bar. On the far right, there is probably a polyethylene bar. You can do that. We use that in non-critical applications, or at the top of a tank or something like that, where it's not a critical seal, but it's more for lightweight. It makes it easy to use, and sometimes it's chemical resistant. So there's several options that you can use in the different bars. But again, aluminum, stainless steel, and 6-inch underwater and 12-inch above water is standard. Here you can see the bolts. This is very standard, a wedge anchor. As you drill the hole, and when you pound the bolt in, you can see that sleeve on the left there is over the narrow part of the bolt. And as you tighten that down, it pulls that wedge up and expands that sleeve and locks it into the concrete. This is the most common design detail. A couple variations of that is a lot of times we will be using epoxy set anchors, especially in applications where you know you're going to use that bar a second time for a liner replacement 20 years down the road. We'll do epoxy set. A lot of times that'll minimize the opportunity for these bolts to spin, but this is very common, and the most widely used in the industry is just the typical wedge anchor. Also, I'm going to mention anti-seize again. That's real crucial. That also can reduce that spinning of bolts from tightening or over tightening. It's really crucial that as you drill these holes, that you blow out and get all that loose concrete out of the bottom of the hole. That can prevent that can change your depth or your effectiveness of the bolt. Also, it's real crucial that you set a good depth, so you don't want to drill too deep or too shallow. So it's real crucial that you use your guides on your drill to get a nice consistent depth depending on which anchor bolt you're using. Yeah, that's it on that slide. This slide is similar to Brendan's slide on the pipe boot as a cutout. So starting from left to right, similar butyl gasket. That's the same gasket that we use on our pipe boots. That really is the true seal. That's and goes directly behind the sheet membrane. In this detail, in this picture, I added a rope hem. And the rope hem will allow for additional strength from tear out. A lot of times we'll do this on floating covers where the cover is going into a perimeter anchor bar that is going to have a lot of movement and a lot of pull and stress over time. That'll prevent any stress on those actual bolt holes. Next is the live rubber. Same thing as the pipe boot. This protects the membrane from the bolts and the bar, but it also actually keeps compression over a long time. So once you torque those bolts to your specified torque, you don't get any compression of that live rubber. So it'll constantly keep that torque for the life of the membrane or the installation. And then the bar, obviously, and the bolts are next. And then on the top right, you can see the sealant similar to the pipe boot, same thing, different sealants, but typically a polyurethane or a Sikaflex. We use a Sikaflex 1A. So there's a standard cutout of mechanical. Next slide. As you can see here, a couple things. So this is these are a couple of interesting things going on in these photos. As you can see there on the picture on the left, at the top of that white membrane, that is actually a mechanical attachment. The reason that has to be there is because it's obviously a square column. You cannot do a pipe boot or use any sort of banding, so you actually have to do a concrete attachment. Concerns I have on drilling into small holes like this or small columns like this is you get a bolt coming in from each corner. You can risk hitting those bolts. You're drilling several holes into a concrete column at one area. But as you can see in this photo, we have taken that liner all the way up, and the reason for that is so we can reduce the amount of bolts we put in at the top in order to reduce the need for a leak tight seal because we're above water level. The slide on the right, this is an interesting one because it has both of my topics for today. It has embed strip and mechanical attachment, and the difference is this is a concrete curb poured around the pond. On the right hand side, you're seeing the membrane attached to an embed strip, And then on the left-hand side, that's where we're going to bring in the floating cover to attach to the mechanical attachment. And the reason for that is number one, on the right, you don't want any bolt holes that cover's got to lay over. So that's why we like to use embed strip, because it's a nice flat surface that cover is going to be rubbing and moving on for many years to come. And we like the mechanical seal here because in the future, when we go in and we replace this cover, you'll actually be able to unbolt that cover and continue to use that mechanical attachment for the future cover. Okay, in this slide, a couple interesting things going on. So this is a use of a concrete curb around a reservoir. This is not a cover going on this one. But the reason for the concrete curb is a lot of times, there's an actual road around the reservoir. This one happened to be paved after we left. It also, if it was a dirt road, it keeps any debris from going down into the membrane or down into the pond. So you can see an anchor trench. We tied the anchor trench in next to the curb. Then they backfilled the anchor trench, and then we came in and did a mechanical attachment and capped over that anchor trench to encapsulate that anchor trench from saturation and once again keeping any soil from getting into the water reservoir. Another thing you can see in the bottom right of the right-hand picture, you can see that chain. This project had a series of ballast tubes attached. And we had a pretty critical design to keep those ballast tubes from breaking and pulling out. So we had to use some significant anchor, and we were actually able to anchor those right into the same bolts on the mechanical attachment. Obviously, a little beefier than a standard attachment, but that allowed us to anchor the ballast system to the mechanical attachment. A couple issues here. I'll kind of buzz through these so we don't run out of time. But here's some examples of poor mechanical or poor structures that we were asked to attach to. You can see, air pockets. Many names in the concrete industry for that. But it's real crucial when you're dealing with mechanical that wherever that bar is going to attach to concrete, you remove all squeeze out between forms. We've got out there and we've been dealing with, ties to the forms, metal ties sticking out of the concrete, pockets of concrete sticking out that are very rough, can damage the liner. Poor concrete where the bolts just will not even hold in it because the concrete is in such bad shape, or we get to a pocket in the back of the concrete. So you see several issues with why this is critical for having good quality concrete. And this is really important when you're dealing with existing structures or relines, old concrete. So a lot of times those will have to be repoured or ground down in the area of attachment to get a good clean surface. Next slide. As you can see here, there's several access challenges. The slide on the left, you can see how are we going to drill that hole. So it's real crucial that either this is poured into one structure or you have enough access to get a right angle drill in there. These are the kind of challenges that we show up to. Design engineers don't necessarily think about when they're putting these together. They're putting these plans together. The picture on the right, you can see there's several transitions, very difficult to attach to, different slabs poured there, so you're getting gaps in the concrete between the two actual pours. And that can, obviously that creates a leak path behind if there's not a good seal. There are some tricks we can use in the industry. We can use some right angle drilling, a right angle drill to get into tight areas. We can also use some sort of sealant or epoxy to seal cracks, that sort of stuff. You'll see some slides coming up on that as well. But these create a lot of challenges. So these are things that need to be considered in the design phase. On this slide, you can see on the left that happens to be a anti-bridging bar because the wall of this structure was lined. And so that the purpose of that mechanical in particular is just to take the stress off the liner creeping down the slope and pulling away from the wall. And then you can see a pipe boot in there. You can see that's actually a concrete stairway going down that we're working under. This is a drinking water reservoir and a clear well situation. And you can just see some of the challenges of doing that. Another challenge you have here is you're bringing two membranes from both sides into that battenous attachment. So you have to increase your length of your anchor sticking out. You have to increase your seals, and you have to get really good, consistent, non-wrinkled material into that mechanical so you don't run into any issues. On the picture on the right, you can see, several corner welding. I mean, this is asking for trouble turning a bar up and having all those corner patches, corner welds, custom fitting, tight access. As some of the testing methods that Brendan showed you, be very difficult to get a vacuum box in between those two structures. So you're limiting your ability to do the quality control on that, on those critical welds in between there as well. On this slide, you can see there's a lot going on here. There's several problems. Number one, you're bringing a membrane up a slope and then turning it up a wall. And the problem with that is your anchor point is 4 inches up the wall from the subsurface. Well, that's on a pretty steep slope. So the minute you pull that liner up there and attach it, that's going to slide down, and you're going to have a gap behind the membrane. If you get any sort of downward force, you fill the reservoir, you get the downward pressure of the water. Inevitably, that's going to put a tremendous amount of stress on that mechanical, if not actually take it to failure point. Also, you can see here the subgrade is very poor. There's pockets of missing subgrade, which is going to create the same sort of bridging effect. Loose subgrade doesn't have good compaction. There's rock in the subgrade as well. And then you can see that L turn, or that turn in the mechanical attachment. That is just going to create so many problems as that pulls down. So it's really crucial that the design engineer understands how this membrane is going to attach to these structures. On the slide, it's pretty obvious what's going on here. In the bottom of the photo, you can see a pipe boot or a grounding wire that is some sort of electrical wire attached to the structure. That needs to be either ran inside the concrete with a water stop seal through the concrete, or it needs to be pulled away from the structure so we can do an actual pipe boot on that. There's no way to attach and get a good seal with stopping that bar and going around something like that. This is a real, common thing we see, especially in tank batteries, electrical substations, that sort of work where you're getting these difficult things to attach to on the side of these structures. Quality testing. Unfortunately, there is not a lot I can say about that. There's not real good ways of actually testing other than a water balance test, and that's actually filling it up and making sure that you don't have leakage. None of the traditional test methods will work on mechanical attachment. And furthermore, if you're going to perform an electronic leak survey, the mechanical causes a grounding issue and can create a lot of false positives with that metal bar in the containment. I better move along here. We're running out of time. Mechanical attachments, keys to success. As we talked about, quality concrete, smooth, uniform surfaces, clean and dry, proper subgrade compaction. There's nothing worse than doing a beautiful mechanical attachment and then the soil settles around the structure and creates some sort of void and pull out. A lot of times it's best if you can pour a footer into the structure so you can attach on the horizontal without turning up. And next slide. Okay, my next one, I'm going to go over embed strip, and I hate this, but I'm going to have to move along quite quickly because we're running out of time. Embedment strips, same format here. We're going to talk about design materials and common problems, and then the key components to success. What embed strip is this actual piece of similar membrane locked into the concrete during the pouring phase. So you actually pour a embed strip into the surface of the concrete, and then you can weld the membrane to that embedment strip, and it replaces mechanical attachment. Obviously, this doesn't work on existing structures. You have to do new pours. It's very crucial that the concrete contractor knows what they're doing. It's a very limited leak path when they're done correctly. And here's a couple details you can see of the embed strip, a cross section, and then the membrane being welded to the embed strip. Here's a couple. This slide shows the two different profiles that we use commonly: 3 inches or 6 inches. A lot of times we use the 6 inch if we're attaching different layers or multiple layers to it. And so it just depends on your design and what you're doing there, and different manufacturers. As you can see here in this tank, we're actually using this to anchor the panels to the wall, and we're welding continuous panels to the wall of the tank. But when the project was done, we had no exposed embed strip except at the top, which was well above water level, because each time we would anchor these to the wall, we would then cut, when we put the next sheet in, we would weld to the membrane liner and then cover that next embed strip. So when the project was complete, there was no embed strip showing. And the reason I like this slide is because embed can be used not necessarily as a seal, but it can be used as an anchoring point. And that is very common for what we use embed strip for. Same picture on the right as I showed earlier with the mechanical attachment. It's going back to the embed strip side of that. This is more of an anchoring point than a seal. This is well above water levels or containment, so really just more of an anchoring point. You can see here, this is the detail that Brendan talked about. I'll breeze through this a little bit. This is very common when you are tying in the membrane liner to the embed strip around the pipe structure. Next slide is a picture of that same thing. And while this is crucial, this is locking in, again, you're anchoring your membrane and you're locking all of your sheet membrane to the concrete pad, which allows that pipe boot really to have zero stress on it and those critical welds that Brendan was talking about. This is by far my favorite pipe boot detail. Since we've implemented this detail when we affect the design, we see very limited problems, and obviously the pipe boots are usually the place to first look if you ever get called on a leak. So this is a fantastic detail, and the embed strip just really makes this possible because you're not putting those membranes over those mechanical bolts. Couple common problems you can see here. It's critical that the embed strip get weld together. If you have a gap in the embed that you're going to attach to, obviously there's a direct leak path between the strips of embed. On the picture on the left, you can see that this was a poured concrete pour, and there was a lot of gapping next to the embed strip, which concerns me that water can actually get behind that embed and then in turn eventually get behind the membrane. So the installation of the embed is very critical, and now you're involving a concrete contractor to something that is very crucial to the seal of the membrane. So it's very important that the engineer and the contractor and the concrete contractor and the liner installer are on the same page to make sure that this is installed properly. Again, next slide. Again, you can see here common problems, no weld on the embed strip. And the welding of this is very simple. You can use a hot plate weld. You can just heat up those and compress them together, and you get a very good lock-in. And when you pour it in and it doesn't have anywhere to move, it has zero stress, and it's a very simple weld, but it's crucial that it gets done correctly. You can see on the picture on the left, we had to go resort to an epoxy to actually seal over those issues, and now your containment is resulting, is all the way down to an epoxy seal, which I do not like. That creates a potential future problem. Next slide, this is just an overall slide of all the issues you can see that we had on this particular project. And once again, this is a liner installer's nightmare, is because now we're counting on a epoxy seal versus, you know, the membrane seal and all the testing that goes into ensuring that membrane is in a good quality state is, in my mind, is kind of out the window because you have all these potential issues. You can see this is real crucial that you don't have cracks. Cracks are, you know, I always say there's two kinds of concrete. There's one concrete that's cracked and there's concrete that's going to crack. So it's real crucial that you get those concrete, you know, that those cracks are not affecting the embed, and you seal those up somehow with a water stop or some sort of epoxy over the top of those cracks as well. So non-destructing testing, you can do a good vacuum test over the embed strip. You just got to make sure that you're not getting false positives from air coming out of the edge of the concrete and the embed strip on the outside. Spark test is always foolproof. You embed the wire behind your extrusion or your heat weld, and then you run down there on that same test that Brendan had showed you. And then the last one is a water balance test, and this is really the only way to, assure that your whole system is leak tight. And the difficult thing with that is now you introduce, how to find the leak. So that's more of a test for the whole system. Embed strip does help with electronic leak surveys compared to a mechanical attachment because you don't have as much metal. But yeah, that's enough there. I know we're running out of time here. Keys to success, same thing we talked about. I'm going to go ahead and breeze through these just because we're running out of time here. So that's all I have. I'm going to turn it back over to Tim.
Okay, great. Thanks, Duff, Brendan, and Pat. We have over 30 questions here, so I'm not sure even where to start, but let me go through a few. We will have a follow-up podcast to answer all of your questions, and we will post responses to all the questions on the website. Also on the screen, there's contact information for Pat Elliott, Duff Simbeck, and Brendan Simbeck, so you can contact them directly. But let's see, we've got 3 minutes. Let me run through a couple of these. What is the water balance test? Whoever wants to take that.
The water balance test is strictly actually filling the reservoir and basically watching to see if you lose any water. A lot of times you'll have to do evaporation pan next to the reservoir to simulate evaporation, so you're not minimized, so you understand your actual loss to, I'm from Colorado, so we can get a tremendous amount of evaporation here. We get high winds, we get hot days, and very arid climate. So that can actually dramatically affect the accuracy of the test. But it's basically just filling it up and seeing if it leaks.
Okay. On this slide, what live rubber would you recommend? Specs of the live rubber, type of rubber, natural, silicone, neoprene, hardness, etc.
Interesting you should ask that, because Brendan and I actually use different ones. He uses a neoprene live rubber and I use an EPDM. I have those. If they want to email me, I can get them over the actual spec. I don't have it in front of me.
Okay, Brendan, you want to jump in on that while I get to the next slide?
Yeah, we really have had good luck with that neoprene, especially when it's captured there or below water. The EPDM is a great idea. I think the two products would work really well, very similar together.
Okay. Next question on the slides, and I'm going to do slide-specific questions because we've got the slides here. On this slide, can you discuss why is the gasket on the outside of the liner material? I've typically seen the gasket on the inside where the tape is located in your example.
So in this cutaway, the butyl tape is actually providing the seal between the outside of the pipe to the membrane liner. That will fill any gaps and give a real positive seal once it's combined with the compression of the stainless steel banding. The neoprene in this case is largely to distribute that confining pressure and protect the geomembrane during the banding process. You know, when you're installing that clip, make sure that you don't have any metal to primary liner contact.
Brendan, and so the light blue here is the pipe, the neoprene's this sort of tan, and then the geomembrane's black, and the cushion is another black, and then the clip, right?
Yeah, no, so the butyl tape is the gray on the furthest left part there. Yes, the blue is the PVC pipe,
Right.
and that tape is actually providing the seal between the membrane liner and the pipe itself.
Right. Okay. Multiple pipe penetrations in photographs. What is the minimum distance that should be provided between the pipes?
The more the better. I mean, really, if that technician can get around completely, you know, the tools we're working with and welding with and testing, you know, are a certain size. So, you know, 12 inches, I would say, is a minimum. That way you can get the welding tool in and around everything. If you need to make repairs, you're able to do that.
Okay. Probably the last one we're going to have time for, slide 53. Once you have that gap in the embedment strip, what can be done to correct that?
Yeah, unfortunately, there's not a lot you can do. The epoxy seal was the only solution that we had on that particular project, and it's unfortunate because all it would have taken was a little bit of good time, you know, and a little bit of you know, forward thinking during the installation of the embed to get that properly sealed. So it is critical that those are welded together. It's very important.
Great. Everybody, thank you for your great questions. Now we probably have around 40 of them. We will get them answered. We'll have a follow-up podcast as well, and that'll be posted on the website, but we'll also post answer to all of these questions. So thank you very much for all these excellent questions. So let me wrap up today, and there's the contact information for our excellent speakers. And our next webinar is by Dr. Rudy Bonaparte, Design and Performance of Hazardous and Low-Level Radioactive Waste Landfills, a 20-year case history of the project near Fernald, Ohio. Visit our website for the installation details that were mentioned and other videos and webinars. Thank you so much for joining us. I want to thank the speakers for their excellent presentation and our sponsors for today's webinar. Thank you and see you next time.